No, wrong thing. That's not the calculator. Let me move it over here. All right, so I just need that little bit in there. So what I'm going to do is a zoom box. So zoom option 1. And I'm going to hit the up arrow and the left arrow until just above the highest point and just left of the leftmost point. And then I'm going to hit enter. And then I'm going to hit the down arrow until I'm just below the lowest point. And hit the right arrow until I'm just to the right of the rightmost point. So it'll box in the thing that you want to take a look at. When you hit enter, it zooms in on just that interval. And if you screw it up and it's a little off, you can go into the window and tweak it a little bit, but this got the job done. All right. So, and you can see the window is very minuscule. You'd have to come up with these numbers on your own, or use a zoom fit option, which, you know, I don't know if it's necessarily worthwhile. All right, so let me snip this in there. So we want the area, so not the volume, but the area. The blue one is the cosine function. I know that for two reasons. One, because the calculator marked it as the blue function when I was typing it in. And two, because I know what a cosine function looks like. And you know, that's the idea. If you recognize what particular functions look like, then you don't get confused when you see something like this. Because you look at it and say, well, cosine always starts off at the amplitude. Right? So it wouldn't be at the origin. But again, when I typed it in, the indicator here was that it was blue, here is red. If you don't have a color screen, then you just want to keep track of which one got graphed first, because it graphs it in sequential order. All right, so I need a couple of things. First, I need to subtract from the dominant, this is the dominant, I'm going to take the cosine function and subtract from it the natural log function. All right, I'm looking at this from the perspective of the x-axis, because basically what's happening here is I have an arbitrary rectangle going all the way up to the cosine, and then another arbitrary rectangle that's only going up to the lower function. Let me get it a little higher. And again, if you subtract those two areas, you'll whatever's left over is going to be what's in the middle. Okay? Because what's happening here, this guy, this rectangle, is just following the bottom one. So as it's tracing, you know, if you were doing this kind of problem with the tech assignment, this is how it would play out. You would populate rectangles below the curve, and then it would give you the sum of all those rectangles. But that's all the stuff that you don't want. When it does this one, it goes below the blue, so it's giving us all this stuff. So taking everything from here down to the x-axis and then cutting away the stuff that you don't want leaves you with the stuff in the middle. All right. The issue here is I don't know where this is going to begin, and I don't know where it's going to end. Well, I don't know one of those two things. It looks symmetrical, so I'm guessing that if I find one, I just have to negate it and I'll have the other. But bottom line is I need this. I need these intersections. I need this location, and I need this one. I don't know if that's one unit. It looks like it's a little off. It could be, but I don't want to take the chance. So, in my calculator, I'm going to hit second, trace. I'm going to select option 5, which is intersect. It, again, looks symmetric, so I could just hit enter, 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 and it's going to drag me to the closer of the two intersections. I honestly didn't care which one it would take me to. So this is good. This is good enough for me. Because if it does have symmetry, then the other one should be exactly the same. You know, and if you're in doubt, let me just paste that. too tiny. I'll just put it like right here. If you're in doubt, if you think maybe it's a trick question where it's just slightly off, then do it again. Second trace 5, and then get over into this neck of the woods. If you want to kind of hop, oh, actually that doesn't work. I thought it would work. It works for derivatives and antiderivatives, so I assumed it would work for this. Second trace 5, it looks like you have to hold it down. You can't hop. When you're doing max and min, if instead of scrolling over, if you just wanted to type a number on that side, like 1 or 0.9 or something like that, it would hop you to that location. I think it doesn't work in this because it doesn't know which curve I want to be on. Right, but anyway, enter, enter, enter. Although it should know that it's the one I'm on. 0.915, so it's the same thing. I'll snip it in, just positive. Let me clean this up a little bit. All right, so we have our bounds, and again, because we're working with respect to x, it's a dx. The low bound, we'll just say negative 0.9, and the high bound, we'll say positive 0.9, but these are approximates that we're writing. We write the approximate, we use the exact, all right? But I don't actually want to have to type that to be a decimal. I'll show you how to handle that in a second. All right, but this is what I need. So you can use shorthand to address the bounds on paper as long as you're using the true thing in your calculator. All right, so we're going to do our math 9. First, I'm going to take note of which of my functions is y1 and which one's y2. I did it before to distinguish the graphs from one another, but now I want to do it so that I can use shortcuts in the calculator. Edit, paste. So, I'm out of here. Math, option 9. We could put the entire decimal in, or actually, before I even get into this, sorry. Let's address the bounds, because we want to avoid writing the decimal. When we did second trace 5 and found the intersection, it said x equals this, y is equal to that. All right, that's this x and this y. All right, so it stored those values in for x and y in your calculator. The problem is when I use the integration function, I'm going to be using x as a variable, not as a constant. So what I'm going to do, and it's like a little nifty trick, is I'm going to take my x solution, just making sure. I'm going to take my x solution and then hit the store key, STO. I'm going to store that in as a. So every time I hit a, which is thought of as a constant, not a variable, the calculator is going to know I'm talking about 0.915. So once I do that, then I'm going to do math 9. My a value is the whole decimal, right? This is negative 0.9-ish, that's positive 0.9. So I'm going to type in negative a, and I'm going to go to positive a. Then in here, I'm going to do cosine is y1, the natural log is y2. So I'm going to do alpha trace y1 minus alpha trace y2. And that's all with respect to x. All right, so all that stuff is to help you avoid having to type stuff in. It's not essential, but it's a nice luxury. If you're comfortable with it, then definitely use it. If you're not comfortable with it, at least try to become comfortable with it, because it may pay off at some point. Because you think about it this way. These are pretty, I don't like this function, but it's not the hardest function to type into your calculator. But when you were learning how to take derivatives with quotient rule and chain rule and stuff like that, like some of those things, when you took the derivative, they became monsters. Like, do you want to type that in every time? No. If you know that it's stored in, like y2, for example, then you can use y2 instead of that expression. And this decimal, I was not eager to type that in. It wouldn't have been a problem, I just didn't want to do it, right? So I recommend at least trying to get to know this stuff. The thing that people get lost with is usually something like this. That's the store key. I've used it a few times in program writing, but it's annoying because it doesn't say on the key what it says on the screen when you hit the key. Right? So that tends to throw people for a loop. So that sideways arrow is how you store. So this answer is stored in an A, and I can use it for whatever I want. So part B, the base of a solid is region R. Each cross section, so we have our region R, that's that mess up there. Each cross section of a solid perpendicular to the x-axis is an equilateral triangle. So we're back to the equilateral triangles. Write an expression involving one or more integrals that gives the volume of a solid. Do not evaluate, right? So, because if you had to evaluate, you're just going to do it in a calculator anyway, right? Because we haven't learned how to integrate natural logs yet. So, perspective drawing. All above the x-axis, right? I'm only going to draw a quadrant 1. We have a symmetrical looking graph here. And it's more than looking, it is symmetrical. So our intersection was something like 0.9 comma 0.6. So let me put a 1 here. 0.9 would be like 0.6 would be like, so something like this. That would be the intersection. We don't really need the intersection. We can just do a ballpark. All right, so something along those lines. All right. Now there's more to this graph. There's a whole other region back here. But let's just focus on this part. Because what it's going to allow me to do when I find my area, if I go from 0 to the approximate 0.9 intersection, I need my radical 3 over 4 times the length of a side squared dx. It would allow me to just double that. That may or may not be advantageous. Actually, I need to put more room in my open parentheses here, but I'll fix that in a second. If you're doing it on a calculator, it really doesn't make a difference. What's the difference between going from negative 0.9 to 0.9 or 0 to 0.9 and doubling it? It's moving forward when you do have to do it by hand. You want to start making use of symmetry, right? But let me fix that real quick. All right, so again, equilateral triangle. So I'm going to have some arbitrary rectangle on the interior that shoots up to become the equilateral triangle that we need. All right, so I need this distance here, which we call S, for the length of the side of the equilateral triangle. Now, a distance between two curves, S, would be equal to the difference between the two functions themselves, dominant minus non-dominant. So cosine x minus the natural log of x squared plus 1. All right, so that's the length of my side. which will get squared to get me my integral. The third dimension is your dx, that's the thickness. So area of the triangle multiplied by the thickness gives us the volume of the solid on this interval. Once we figure out 0.9, double it, and you have the whole distance, or you can go negative 0.9 to positive 0.9, up to you. All right. Now, for giggles, even though it said do not evaluate, I'm going to do it anyway. Because our bounds are pretty much established. I stored it in as A. I want to make use of that. So I would do 2, math 9. We're going from 0 to the A value that I stored in. You could multiply the root 3 over 4 times the 2 and come up with root 3 over 2 as a coefficient, but I didn't do that, so I'm going to go this way. All right, so cosine, which is my y1, minus the natural log, which is my y2, quantity squared dx. All right, so you get that. Now, if you didn't want to go the doubling route, if you wanted a different integral, but accomplish the same thing, you could go the negative a to a. Get the same thing. All right, so a bunch of different avenues that you could take. But this is the one that's consistent with this.